So guys, we'll go to our next speaker. Actually, let me present you one of the most important people in the CT community, and every time in his presentation, I have too much expectations because from my point of view personally, his presentation skills is outstanding. Since the first time I started in ASPE in 2018, he shows some things about cats and stuff like this, and it's mind-blowing. So please let me introduce Herminso from Zeiss here.
Thank you for the kind introduction. You're putting the bar quite high, very high. I wasn't prepared for that. And I don't have pictures of cats for you today. Sorry about that. I'm becoming a little more professional. Not like when I was a student at UNCC. I could have all the one I want. But now I work for Zeiss. It's very nice to have this presentation right after Nicolo's presentation. So I get, he did all the hard work for me already, so I get to skip a lot of the long preamble about what CT can do for metrology and so forth. So let's dive right into the topic. I'm going to talk about multi-scale X-ray imaging, talking about different dimensional scales. And just as a motivation, we all know the challenges that we have with qualification or quality assessments of additive manufacturing parts. We know they are complex freeform shaped parts. They have high surface roughness, internal geometries and undercuts, voids, entrapped particles, and so on. And there are several technologies to do quality inspection, the traditional dimensional metrology, CMMs, for roughness or dimensional analysis. CT, we already hear about that. The great thing is non-destructive inspection. And we do have other technologies like microscopy or electron microscopy, which are great in terms of high spatial resolution, with the disadvantage that they only can see in the surface. And if you want to use electron microscopy, for example, then you have to cut the part and prepare the sample, a small portion of the sample to put it inside of the electron microscope. If we now focus into non-destructive inspection technologies, CT is not the only one technology out there. There are other technologies like ultrasonic, eddy current, but CT has the main advantage of having a long penetration range inside of the part or the component, and also having a great spatial resolution as compared to the other non-destructive techniques. Now, if you want to do multi-scale imaging, let's say going from the nanometer range all the way to centimeter range, then it might not be sufficient with a single X-ray CT system. There are trade-offs among them in terms of high energy range or nano imaging capabilities. So there is macro CT and micro CT. That's where most of the work in dimensional metrology falls. And then there are other technologies, nano CT for high resolution imaging, and of course synchrotron CT, with the disadvantage that then you have to schedule beam time in an accelerator, and you have to wait months for that. So the ideal situation is that you can bring those capabilities to the lab. We know how CT works, mainly from the previous topic, but I like to introduce a step further, which would be X-ray microscopy. The CT technology is quite simple. It's based in geometrical magnification. You project a beam of X-rays into the sample that projects radiographies into a flat panel detector. But that can get used only so far in terms of spatial resolution, because it depends on the size of the sample and where you locate the sample in that cone beam. If you add a set of lenses and instead collect the X-rays in a scintillator before they are converted into light and pass through a set of lenses before going into a CCD detector and creating a gray image, then you can take advantage of optical magnification. Just like in a light microscope, you can change the zoom in of those lenses and then target different regions of interest at higher resolution. The trade-off, of course, is the field of view, as in a light microscope. If you increase the resolution, you diminish the field of view. And that's how you can use multi-scale imaging. You might need to use different systems, one to collect macro scale imaging of a component, and then if you see things that are of interest, you can then zoom in with an X-ray microscope inside of that part and collect images at a higher resolution. If you still want to go further, you might prepare the sample. Let's say you can isolate the section where the defect is. You don't have to slice right through where the defect is. You can preserve that, but you can collect that chunk into a nano CT and get a higher resolution. And you can scan for all the processes from the powder to the finished good to correlate where in the process the degeneration of the part or the defects are being created. So why 3D X-ray tomography? A great summary is you can create a digital twin, you can work with that, you have all the 3D data there, you can do simulations with that, it's non-destructive, and it's complementary to other techniques, such as electron microscopy. If you're not satisfied with the resolution, at least you got an overview, you know where the problems are, and then you can cut the sample with a laser or use a ion beam laser electron microscopy. In terms of metrology, I'm not going to go too deep into that. We already saw what Nicolo has done, and I have published quite a lot with Professor Smith from my work at University of North Carolina. But the basic idea is that they knew how to do some sort of calibrations, and that's the main differentiation as an X-ray, as opposed to a classical X-ray imaging, because you need to convert the imaging or the voxels into a dimension, and that dimension is to be corrected somehow for deviations, and then now you're more confident you can do dimensional metrology. Once you are confident that your system can do that, then you can do all kinds of comparisons against a CAD model. You can do all kinds of studies in terms of cell volumes of different sections of your additive part, and change the parameters and evaluate how it goes. You can do simulations or verification to predictions from CAD models, so you can have a scan, you can convert that into an STL, so basically that's the data that represents the part, do some kind of pressure or force simulation and see how it compares to as designed to the CAD model, and you can track or verify the accuracy of those models to see if you can get away with the CAD simulation instead of having to scan the part. But this is a nice way to verify that. Nicolo has mentioned some additional work which I've done in collaboration with some students and professors in Spain. And Yvonne Olgado has done some interesting studies in terms of checking the thickness evaluation of through-hole detection. And more interestingly, which she has shown, is the study of traceability of porosity. We have known for ages how we can do porosity evaluation with CT, but the question is, or the question still remains, how accurate are those computations when people are telling you your part has this much porosity, or this pore has a given volume and dimension. Have they done the right sort of calibrations to make sure that those dimensions are accurate? So we bring or we borrow techniques or concepts from the dimensional metrology world to try to do assessments in those calibrations. Again, you can just read the papers that have been published. The other thing that can be done is with a set of parameters that you are doing with coupons, you can evaluate several tens of coupons, and then you can CT scan and evaluate them for porosity or for dimensional metrology, and try to optimize where in terms of the volumetric energy density of other parameters is your optimized part. This is also something we probably have shown before, and it has been published, but the basic idea is that you can try to optimize printing parameters like velocity, power, or others to minimize the level of defects of porosity inside of the part. But the reality is when you try to do CT measurements, you strongly depend of the resolution, the imaging resolution. And the resolution in reality depends of a bunch of parameters, which I'm not going to go into here. We also have published that in precision engineering with Professor Smith. And he also has designed with some of his students some artifacts to verify the resolution of a CT system as long, and also some of the work done at the University of Padua. But basically, the X-ray source can be an influencing factor, but also the imaging detectors. And if you want to increase the resolution, as I was mentioning at the beginning of this presentation, you can opt for alternatives from the flat panel detection, which is optical magnification that bring high resolution capabilities because you combine optical magnification with geometrical magnification. And the ability to zoom in and do registrations of regions of interest into the full volume allows you to kind of point directly, even in the reconstruction, where you want to go, and the system should be able to go. If it is well designed, should be able to get you the portion that you are interested in at high resolution. So just like any microscopy tool. And you're very familiar with additive manufacturing, so you know what they can do. They can do inspection for structural integrity, internal defects, porosity, surface roughness. And once you have the data, you can do all these kind of cool videos where you can see the three-dimensional data with all the porosity, particle inclusions, or powders that haven't been melted during the process. This is really one of the most cool advantages of using CT is that you can see all of that information, and it's very visual, which is easy to understand. Enough about talking what the capabilities of X-ray microscopy are. I want to get into a new topic that we have been working on, and is very relevant nowadays, is the use of artificial intelligence in X-ray imaging acquisition. With the presentation from Nicolo, you already saw how to use machine learning for post-processing, trying to infer data from the trends or from labeling. But what we are doing here is before the reconstruction. And the key questions here is, okay, trying to do multi-scale imaging with X-ray is a bit challenging because you have to explore different target regions. You can optimize the imaging conditions, but you can get into a very long scans. When you get to high resolution, you also get a lot of noise. And that's due to the nature of the X-ray behavior. So the question here is, can we improve the way in which we are doing the traditional way of reconstructing to get rid of noise that can be easily predicted from the X-ray imaging or the algorithms we are using, and then extract the data without getting rid of the data, without smoothing the data, without creating false positives or so. And the key idea is, let's go back to the traditional way of reconstructing, created in the 1980s by 3 people that used to work for 4 out of the Detroit office. And this is the same algorithm that everybody is using today. It's very mathematical, it's optimal for the geometry, and it's very powerful. But we have now new technologies that can improve things. The disadvantage of the traditional analytical algorithm is that you need a bunch of projections, more than 1,000 or 2,000, to be able to create a decent image quality in the data. So the scan is slow, and still you might have some noise in the data. What if we use deep learning to learn where the noise is generated from the projections to the 3D volume, and then get rid of the noise during the reconstruction to enhance the quality of the data? And there are some examples here. If we collect over 1,000 projections with the standard reconstruction in a metal additive manufactured part, if we try to reduce to speed, then you see all the noise, aliasing artifacts, etc., or undersampling. If we train an algorithm that learns where those artifacts come from, we can get rid of them and then save the data. And this has a great advantage as opposed to post-processing algorithms because you preserve small features. It doesn't get rid of them when you try to use like Gaussian or smoothing algorithms, might get some data out. And if you speed the scanning, you also get a very decent type of data with all the information that you need there. And when you try to do this with multiscale imaging, then you take advantage of the high resolution lenses, which would be longer scanning, but you would be able to speed up the scanning when you try to do this with, let's say, a 40x type of detector and combined with the deep recon. You can try to implement this for in situ studies, which will speed up the ability to collect more data in less time because you're taking advantage of this particular algorithm, and when you can only collect some data points with FTK, you can collect much more with deep learning algorithms when you do this type of in situ studies. The time for the scans are there, no need for me to mention. Maybe the only other thing I want to mention here, which people are always asking, yeah, but you're creating this black box, how does it work? Yes, we are a commercial company, cannot tell you all of what we do internally, but we are enhancing the software for the user experience so you can have an idea to compare. I mean, I encourage you to do your own comparisons, but the idea here is if your model is working correctly, when you do the subtraction from the image generated from deep recon in this case as compared to the classical algorithm, all you need to see is noise. If you see some type of structure, then it means the model is not right, because then it's getting rid of features or creating features, which you don't want. And you can have more information on this in terms of the number of events, of the convergence of the algorithm, etc. So you can do all of that. Okay, now I'm gonna speak about a second way of taking advantage of these deep learning algorithms. The first one was about reconstructing data, getting rid of noise from the projections to the 3D volume. Now, there is a big challenge when you try to do large field of view. And the question is, how can we take advantage of deep learning? What if we train a high resolution scan in a small field of view and we expand that to a large field of view that has more or less similar features? And that can be done then with a couple of scans instead of spending a lot of time of doing multiple high resolution scans and stitching them together. And there are examples here. You can see the the traditional type of scanning, the high resolution scan, and then the deep scout model. And you can expand this to the full network from a small region of interest training to the full type of scan. And you can quantify this in terms of the impact when you do now calculations of porosity, how much more porosity you can calculate, or the clarity of the data you are getting. Now the question is how I'm sure that I'm not generating fake data. This is not generative AI, it's getting rid of noise, and you can use electron microscopy to do verification. As you can see here, you can see those 3 voids that were detected with Deep Scout right in this image. This is a nice way to verify, and again, I encourage you to do all the verifications. Let me summarize here. I did a quick introduction of the utility of this technology for 3D non-destructive inspection. I gave you some examples on how to use the digital twin technology for additive manufacturing improvement, and some mention of metrology, leveraging the presentation from Nicolo. And lastly, how to take advantage of deep learning algorithms to improve not only image quality, but speed up the scan time that you can get with X-ray computer tomography or mass microscopy. And with this, I'm gonna leave room for Questions? I think you were asking for my cat. There it is.
Oh, thank you very much for the wonderful graphics and the cat. So, in 2014, I had a paper with Zeiss, Mars and Pausa at the time, and we were looking at using CT for looking for both pores and also geometric defects. And we were very concerned about beam hardening with thicker pieces, but instead we defaulted to using lattice structures as the demonstration to avoid the beam hardening concepts. And I'm still seeing a lot of examples with lattice structures. Can you elaborate over the last 14 years, how far have we gone to looking for defects and understanding the uncertainty of finding those defects with thicker parts?
Mm-hmm. So the beam hardening algorithms corrections have been improved since then. I mean, there's a lot of development. This is still a pain for users. Then the idea is you have to try to design the parts in a way that you don't have a strong effect on those artifacts, or change the orientation of the part to avoid them. In terms of uncertainty, qualification of all these kind of defects, there has been some progress. Lots of what I did with the storage mate wasn't based on dimensional methodology, but there's been quite a bit of progress in trying to implement some of those ideas into porosity computation. That's some of what the University of Padua is doing, and some of the references I show you, I just encourage you to follow through those. It's not a job done. There's a lot to do, but the initial steps have started.
So thank you for the wonderful presentation, as usual. I have a question on the deep reckoning algorithm. Have you evaluated also the uncertainty and also the variability you have in the reconstruction when you are changing, for example, the shape of the part and the material?
Yeah. So regarding, I'll start with the second part of your question. If you change the part, if you change the material, you have to create a new model. You cannot expect that a model that you create, I don't know, for polymers is gonna work in metals. The principle is the model to work without creating a new model each time is ideal for repetitive type of samples or with some homogeneity in the structure. The second one, in terms of the uncertainty, depends how we define it. If we define it from the point of view of the algorithm designers, that we can draw some parameters in terms of the number of events and the convergence of the algorithm. If you're talking more about the rigorous uncertainty quantification from the methodology community, that's another topic. We haven't done anything yet, but we welcome people to start doing that.
Yes, just one question. I was asking about the uncertainty because lots of machine learning began to generalize to the synthesis. Yeah, I'm gonna ask another question. This is about the points per function. Just one of your slides you you got Foxport and you got points per function, and you also got the voxelization which is connected with the detector blurring. So have you made efforts to modeling this blurring from Foxport and also the detector pixel blurring, and in a way that is there a way to kind of go backwards? Can we do deep blurring to improve the resolution?
Yes, that's the second part, the very last part I presented. So if it wasn't clear, the first one we call deep recon, which is to do the reconstruction. The second one is for deep blurring, and that basically uses the point spread function in the algorithm that has into account all the geometry and the detection technology compressed in the point spread function to try to deblur that from a high resolution type of data by seeing what a low resolution data looks like, and then spread that deconvolution or deblurring through the full.
Yeah, we're also doing similar work that we think that points per function of Foxport is a linear operation, but the detector pixel blurring is kind of non-linear. So non-linear basically means you kind of go backwards. So some research work required.
Yeah, so far what we are using is not just depending on the system, it's also depending on the part and the geometry of the part. But we can certainly talk more about that
sure.
during the
Yeah. Okay.
Okay guys, I think we have to thank our speaker because we're running out of time now.